3D transformations. In the last class we introduced the different standard transformations. The first was translation, and we said that translation can be captured by the transformation matrix, which looks like this. Okay, this is a 4x4 transformation matrix in homogeneous coordinates, which will translate a point by a vector tx, ty, tz. Okay. Then we said rotations, and let us say rotation about the z axis would be captured by this matrix. Okay, where C stands for cos theta, S stands for sin theta. Okay. Similarly, we said rotation over the x axis would be captured by and rotation about the y axis would be captured by the transformation matrix, which would look like this about the y axis. So 0, 1, okay, and then for scaling we mentioned a matrix like this. Okay, where if you want to give a uniform scaling by a factor of s, we will only change the homogeneous coordinate. If you want to give a non-uniform scaling in the x, y and z direction, we will use Sx, Sy and Sz in the 3 diagonal terms corresponding to the x, y and z directions. Okay. And we also mentioned that if we have a general 4x4 matrix like this, then in this 4x4 matrix, this corner term is a homogeneous coordinate which controls the uniform scaling. These 3 terms control the translation matrix. These 9 would control the different rotations about Rx, Ry, Rz. All 3 of these will be controlled by these 9 terms. Then these 3 diagonal terms will control the scaling in the x, y and z directions. These 3 terms we haven't yet talked about. These will control the projections and how they will control the projection, that we will see later on. Okay, so out of these 16 terms, these 13 terms will control the different transformations that we have already seen, that is translation, rotation and scaling. Then last time we also saw that if you want to reflect about any axis or about a plane, that can be done by changing the scale factors in the 3 directions. Okay, by giving either 1, 2 or all of them values of -1, we can reflect about either an axis, about a plane or about the origin. Okay. Today we will talk of rotating any arbitrary point about any arbitrary axis. Okay. So if we have there the xyz axis and we have any arbitrary point xyz, we want to rotate it about an axis which is passing through the point DEF and has direction cosines of ABC. Okay, that is a general arbitrary rotation about any axis. We already know how to rotate about the x axis, about the y axis, or about the z axis. For carrying out this rotation would be carried out in a sequence of a number of steps. The first step is translation, so that this point DEF will now become the origin. Okay, a new coordinate system would be passing through this point like this. Okay, that it would involve a translation by an amount of minus d minus e minus f. Okay, so the first step is a translation step. Okay, and that this would be carried out by a transformation matrix which would look like this. Okay, this will call as T1. Then the second step will be rotation. Okay, and the first rotation that we will carry out would be a rotation such that this direction vector ABC will now be rotated, let us say, about the z axis, so that it will now lie in the zy plane. Okay, we will rotate it so that it will now lie in the zy plane. Okay, we can rotate it so that it can lie in any of the three planes. Okay, I can, let us say, if you look at it from the front, this is one axis, this is the second axis, and this vertical is the third axis, and we have a vector like this. Okay, I can rotate it in this manner. From this point, as I will rotate it in this manner, the angle by which it will be rotated will be an angle which I will be seeing as a projection in the bottom plane. Okay, I will again repeat, if I look at the top view of this vector, if I look at the top view, whatever angle I see in the bottom plane, that will be the angle by which I have to rotate this vector so that it will come into this vertical plane. Okay, and this rotation is being carried out about this vertical axis. Is that all right? Okay, so what we will do is, this is my point A, B, C, and this is the origin. This is the new origin after I have already done the translation in the first step. Okay, as a result, this point has now become the origin. Okay, and this ABC is the direction vector for the axis of rotation. Okay, this gives the direction cosines for the axis of rotation. So I will take this vector ABC, and now I am looking at its projection onto the YZ plane. Okay, I am planning to rotate about the x axis. So its projection on the YZ plane would look like this. This would be the projection onto the YZ plane. This diagonal, what will be the magnitude of this diagonal? Okay, the direction cosine of this vector are ABC. So now the projection, this will have the coordinates of, it's a projection onto the YZ plane. So the x coordinate will be 0, and the y and the z coordinates will be how much?
Cos.
B and C. Okay, because the coordinate, this has coordinates of ABC, So the y and z coordinates of this would be BC. Okay, basically projecting a point ABC onto the YZ plane. Again, if you look at it on this table, this is one axis, this is second axis, and this is my third vertical axis. If I have any point like this and I take its top view, this point has coordinates of ABC. When I project it onto the YZ plane, its x coordinate will become 0, the other two coordinates will remain unchanged. Okay. So this will have coordinates of 0, B, C, which means this distance would be C and this distance would be B. Okay, and this diagonal, let us say, would be lambda, where lambda will be equal to square root of B squared plus C squared. Okay, and how much will be this angle? This theta would be tan inverse of C by B, or we can say that sin theta would be equal to C by lambda and cos theta would be equal to B by lambda. Okay, that is for this angle theta. Okay, but now you have to be careful that we have to rotate such that this vector will now coincide, let us say, with the xy plane. We are rotating about the x axis so that this vector now coincides with the xy plane. Okay, so by what should be the angle by which we should be rotating our axis? Theta or minus theta? Minus theta. You have to be careful in answering that. If I take this vector and I rotate it by an angle of theta, what will happen? It will again go theta in this direction. I don't want that. Okay, so if this is my vector, I will have to rotate it by minus theta so that it will now lie in the xy plane. If I have to rotate it by minus theta, for the sake of my transformation, let us say my theta prime for transformation is equal to minus theta. So I will get sine of theta prime will be equal to minus C by lambda and cos of theta prime will be equal to B by lambda. Okay. So for this step, my transformation matrix, what would that look like? I am rotating about the x axis by an angle of minus theta. So this will be 1, 0, 0, 0. This term is cos theta, which is B by lambda. This term is sin theta prime, which is minus C by lambda. This would be C and this would be B, and I can have 1 by lambda outside. Sorry. Okay, so this would be a transformation matrix, after which my axis of rotation would now lie in the xy plane. Okay, so I will repeat here, this is rotation about x by an angle of theta prime, and this is given by the transformation matrix that I just wrote. Okay, after this stage, this vector is now lying in the xy plane. Okay, so if I draw another figure, earlier my vector with respect to this origin looked something like this. Now it has been rotated so that it will now lie in the xy plane. Okay. So my vector now lies in this xy plane. Okay, and since this vector has been rotated, what is the length of this vector?
Same.
The length would be same unit. Okay, since we said ABC are the direction cosines, it has still got unit length. Okay, and what will be the coordinates of this point? Let's look at this.
AC. A0C.
A0C. Are you sure? If the coordinates are A0C, the length will not be 1. You'll have to normalize it, but what will it be? Just have to visualize it. I have rotated it about the x axis so that this vector has now fallen onto the xy plane. Okay, a vector again, if you are looking at it from front, these are my 3 axes, this is the vertical axis. A vector like this has been rotated and it is coming to this plane. So now in this plane, I want to find out the coordinates of this point. This vector is like this, it is coming like this. To the xy plane.
A by root over a square plus b square and b by root over a square plus b square.
So this point has a distance of 1, but how much is this angle?
The x coordinate will remain the same.
The x coordinate will remain the
Same.
x coordinate will remain the same.
Yeah.
Why?
Because we are kind of rotating it about, say, the x axis.
When we took this vector, we rotated it about the x axis. Okay, so if I am taking this vector and rotating it about the x axis, the x coordinate remains the same.
You can find the y coordinate out now.
So the x coordinate is how much? So the x coordinate, that is this distance, would remain to be a. Is that okay? See, I have even written the transformation matrix over here. I had a vector like this which is rotated onto the xy plane. The rotation is about the x axis. If I rotate any point about the x axis, its x coordinate remains unchanged. Okay, so I take the tip of this vector, which is the point ABC, and I am rotating it about the x axis. So the x coordinate will remain unchanged. Okay, and the z coordinate will of course become 0. Okay, so the x coordinate is now unchanged. Therefore, the x coordinate will remain at 1. And what will be the y coordinate? Under root of 1 minus a squared, which is the same as under root of b squared plus c squared. Okay, which is the same as lambda. If you look at this figure, under root of b squared plus c squared is the same as lambda. Okay. So in this figure, when a vector is now in the xy plane, the x coordinate is a and the y coordinate will be lambda. Okay, and if I am looking at now, if I want this angle, this is my z axis. If I want this angle, what will be cos of that angle and what will be the sine of that angle? The sine of that angle is lambda divided by 1, okay, because this 1 is the diagonal and this angle is 90 degrees. Okay, so sine of this angle will be lambda divided by 1 and the cos of this angle will be a divided by 1. Okay, cos theta will be equal to a. Okay, and now I want to rotate this vector about this z axis, let us say, so that it coincides with the x axis now. Okay, again that will be rotation by minus theta. Okay, so by rotation by minus theta would give me a transformation matrix which would look like this. Again about the rotation about the z axis. So cos theta is a, sin theta is minus lambda, lambda a 0 0. Is that all right? So after this second rotation, after the second step, a third step will also be a rotation, which is rotation about the z axis, let us say by an angle of alpha, such that the transformation matrix would be a minus lambda, lambda a 0 0. Okay, and after this stage our axis of rotation is now coinciding with the x axis. Okay. Once the axis of rotation is coinciding with the x axis, the next step is to rotate by an angle of, let us say, theta about the x axis. Okay, and that is given by this is cos theta, sin theta, minus sin theta, cos theta. Step 5 would be reverse of step 3, okay, which will be RZ alpha inverse. Okay, step 3 was this rotation, the reverse of this will be inverse of this. Okay, and that will be obtained just by a minus lambda here and a plus lambda here. Okay, that will be step 5. Step 6 would be reverse of step number 2 and step 7 would be reverse of step number 1. Okay, this would be Rx theta prime inverse and this would be T1 inverse. Okay, so now the complete transformation will be obtained by this is T1, this is T2, this is T3, this is equal to T4 the complete transformation will be obtained by T1, T2, T3, T4, T5, T6, T7 or okay. So by this complete transformation we can rotate any point about any arbitrary axis. Is that alright? One thing you have to keep in mind is that while carrying on the rotations, in this case we first rotated about the x axis so that it came into the xy plane, and then we rotated about the z axis so the vector came along the x axis. Okay, I have aligned this vector along the x axis. There is no reason why I should align along the x axis. I can align it either according to either with respect to the y axis or with respect to the z axis. If I align it with respect to the y axis, then the rotation will be about the y axis. If I align it with respect to the z axis, my actual rotation will be with respect to the z axis. Okay, I can do it either way. The sequence of rotations is also immaterial. The final transformation matrix will remain the same. Okay. Any questions with respect to this generalized rotation? Okay, then the next thing we will now talk about is what is referred to as projections. Okay. If you have any arbitrary point x, y, z, okay, and we project it onto the yz plane, we just saw it, its coordinates would now become 0, y, z. Okay, that is simple projection onto one of the orthographic planes. Okay, but we also have other kinds of projections. Are you aware of what are the different kinds of projections that are there? Orthographic projections, oblique projections, isometric projections, perspective projections. Okay, if we have any parallel projection, okay, we will consider a case where it will be either orthographic or it will be oblique. Okay, do you know the difference between orthographic and oblique projection? Orthographic or an oblique projection, what is the difference between the two? How do you define an orthographic projection?
Three perpendicular planes. The projection takes
Projection on the three perpendicular planes. Isometric projection, is that a orthographic projection? Okay, firstly, what is a parallel projection?
So when you view from an infinite distance,
When you view from an infinite distance, so then what happens?
then all the rays that you get are essentially parallel instead of being converging.
Okay, so all the projecting rays, projecting lines are parallel. Okay, that is a parallel projection. A parallel projection can either be oblique or it can be orthographic. When can it be when is it called orthographic and when is it called a oblique projection?
The one you have there is oblique.
When what is
What you
oblique?
have there is oblique.
What I have here is oblique.
Yeah, like
when the observer is at normal to the coming rays, And if it is at an angle.
Okay, I'll give you the definition. In an orthographic projection, your projecting rays are perpendicular to the projecting plane. Okay, if you have any object, let's take a simple block like this. Okay, and I take parallel rays from it for the sake of projection in any direction, and my projecting plane is taken perpendicular to it, then I get orthographic views. Okay, the three standard orthographic views that you see, the front view, the top view, or the side view or profile, these are obtained when the projecting plane is either perpendicular to the y-axis or perpendicular to the x-axis or perpendicular to the z-axis. Then you get your standard orthographic views. Okay, but orthographic view is a general view in which the projecting lines are parallel to the projecting plane. Okay, all the projecting lines are parallel and the projecting lines will be perpendicular to the projecting plane, like in this case. In the case of an oblique projection, my projecting lines can be at an angle to the plane. These are my projecting lines, but my projecting plane can be at an angle. Okay. In contrast to parallel, we have another kind of projection which is called the perspective projection. In a perspective projection, the observer is at a finite distance. Okay, so the projecting lines are not parallel. Okay, if we have a or let's take a view like this. And we have an observer who is here. This observer, the lines that are coming to him, the projecting lines would be something like this. Okay, the projecting lines coming to him are not parallel.
3D.
It's a 3D effect. Okay, let's say if you're a very standard example given is if you're standing on a railway track and you look at the railway track would look something like this. At infinity, it will seem to converge to a point. Okay, even though the lines are parallel, very close to you, the distance between them will look to be larger than the distance at a very far away point. Okay, that is the perspective view of the railway track. Okay, in this case, the projecting lines are not parallel and they appear as if they are all converging at a point. So we will see the perspective view in detail later on. Let's first talk of the parallel or the orthographic views. Okay. Let's talk of an orthographic projection on any arbitrary plane. Okay. This is the plane that we are talking about. This plane is passing through a point x0, y0, z0. Okay, and its unit normal vector is given by L M N. Okay, now if I take any arbitrary point and I want to project it onto this plane. Okay, mind you, right now I am talking of an orthographic projection. Okay, so my direction of projection is going to be the same as the direction LMN. Okay, because my direction of projection is going to be perpendicular to this plane. Okay, so this point, which is some point x, y, z, will get projected onto x prime, y prime, z prime. Okay, now this point x prime, y prime, z prime would lie on the projecting plane. Okay, and the projecting plane is given by a plane which is passing through the point x naught, y naught, z naught with direction cosines of LMN. Okay, so now we want to find out this point x prime, y prime, z prime. How do we do that?
Bring the XY plane there with the origin.
Line
in
of
the given
plane
point.
with
We bring the xy plane onto this projecting plane. Okay, let's say this is x, y, z. And how do we align? This is my original origin of my xyz coordinates, and this is the point through which the plane is passing. Okay, so in step 1, I will translate so that this becomes the new origin. Okay. If this becomes the new origin, my translation is by minus x naught, minus y naught, minus z naught. Okay. In my step 2, I now rotate my axis such that this plane becomes the same as the, let's say, the xy plane. Okay, or my z axis will now start coinciding with the LMN vector. Okay, so I'll say rotate such that z axis becomes identical to the direction vector LMN. How is this rotation performed? It will again be a sequence of 2 rotations, the way we just saw in the other example. Okay. In step 3, we will project the point xyz onto the xy plane. Okay, that is project on xy. And how do we project on xy? We just put z equal to 0. Okay, this transformation matrix will project it onto the xy plane. Okay, and then steps 4 and 5 would be reverse of steps 2 and 1. Okay, so by a sequence of these 5 transformations, we will be able to get the orthographic projection of any arbitrary point xyz on any arbitrary plane. Is that alright?
all these transformations are being done on the point with a direction cosines of this element.
Again, please repeat.
All these transformations
Yeah.
are being done on the point xyz with
Yeah.
direction cosines element. Is it so?
The point is xyz. Okay, LMN is the
Of the plane, but it will be of the
LMN is the direction of the projecting lines. Okay, LMN is the normal vector for the projecting plane. Okay, so what we are doing is we are first translating the origin so that my axis would now look like this. Okay, then I want to rotate my coordinates such that LMN coincides with the z axis. Once that happens, this would look something like this. This is my z axis, and my x and y axis will probably look something like this. Okay, so whatever be now the coordinates of this point xyz, I can easily project it onto this plane just by ignoring the z coordinate.
But we need to do similar transformations on that point too.
Yeah, all these, okay,
All these are done on the point.
all these transformations are done on the point. So let's say we get transformations T1, T2, T3, T2 inverse and T1 inverse. If this is a point P, my point P prime will be equal to P multiplied by all this. Okay. So this is how a orthographic, a general orthographic projection can be obtained. Okay. Let's now take another example, which is a general parallel projection. Okay. In a general parallel projection, we have any arbitrary point xyz, okay, and we want to project it onto the xy plane. Okay, this is the xy plane, but now our projecting direction is not perpendicular to the projecting plane. Okay, I am talking about general parallel projection, not necessarily an orthographic projection. So a projecting direction is a direction given by LMN. Okay. If I project this point in the direction of LMN, I will get some point on the xy plane, which is, let's say, x prime, y prime, z prime. I want to get coordinates of x prime, y prime, z prime. Okay. In the earlier case, our projecting plane was perpendicular to the projecting lines. So when I was projecting onto the xy plane, I simply putting the z coordinate equal to 0. But now I want to project in the direction of LMN. It can be an oblique direction. Okay, how will we get the coordinates of x prime, y prime, z prime? Any ideas on that? Anyone?
Translate projection on a plane which is passing through the point x dash, y dash, z dash with.
Again, please.
It's projection on a plane which is passing through the point x dash, y dash, z dash and has a normal vector element.
But we don't know x dash, y dash, z dash. We have to find out x dash, y dash, z dash. We can't find out the projection without that.
You know the line. You have the initial point and the direction cosine.
Yeah.
So you can find out the point of intersection of that line.
Correct. We know the initial point of the line. We know the direction cosine of this line. We can write down the equation of this line, and we know the equation of this plane. The intersection of the two will give us this point x prime, y prime, z prime. Okay, in this case, I should not try to translate my xyz axis onto this point and then rotate the axis and so on, what we were doing in the earlier cases. That is not necessary. All that we have to do is, we know the point xyz, we know the direction cosines, we can write down the equation of the line and we can find out its intersection with the xy plane. Okay, how do we do that? Let's, okay, just for the, if I write down the parametric equation of this line, what will that look like? Any point on this line will be given by x plus t times L, y plus t times m, and z plus t times n. Is that okay? Yeah.
So till now, it seems that we are trying to avoid writing equations and solving them.
Yeah.
We were always doing some of the other manipulations to avoid this.
Yeah.
So here, why do we have to do it?
Okay. It so happens that here this is simpler. That's all. So far, when we were trying to rotate the axis and so on, it was simpler to do that. Finding out the coordinates using the intersection of planes and all that would have been very complex. Okay. For example, if I take up this case itself, if I try to write down the equation of this plane and the equation of this line and find the intersection, yes, I can do that. Okay, but that will be a bit more complex than following this method. Okay, in this case it so happens that the equation of this line is quite straightforward, the equation of this xy plane, that is also very straightforward. Okay, the parametric equation of this line is simply this. Any point x will be given by x plus TL, the y coordinate of any point will be y plus t times m, the z coordinate will be z plus t times n. Okay, and for the intersection with the xy plane, we will just have to put that this has to be equal to 0. Okay, if this has to be equal to 0, t is equal to minus z by n. Okay, so we will get the point x prime, y prime, z prime will be equal to x minus L by n, comma y minus m by n and 0. All that I have done is t equal to minus z by n, I have put that over here. Sorry. Okay, so x prime, y prime, z prime will be x minus Lz by n and y minus mz by n and 0. Okay. I just repeat that over here. And this again I can write it in the matrix form using homogeneous coordinates as what will be the transformation matrix? X prime is equal to x minus Lz by n. So x will have a 1, there is no term of y, and z will have minus L by n. Similarly, y prime is y minus mz by n, no term of x, this would be 1, this will be minus m by n, and this would be 0. And z prime is 0, and the homogeneous coordinate h should turn out to be 1. Okay, so this is a transformation matrix for a general parallel projection. Okay, where my projecting lines are at an angle of or have the direction cosines of LMN, and my projecting plane is the xy plane. Okay. Any questions on this general parallel projection? Okay. In that case, we'll stop here now. The next class we'll see other types of projections. Okay.